Anybody have any questions? I think everybody in here has told me which modules you want to do, but I'd also like to know what standard you're going to do your presentation on sometime in the next week or so. If you need to come sit down and talk to me about it, I'd like to know, because I don't want someone taking a big broad standard that's going to be too broad. I'd like to take a simple standard. I mean, the guy who did the bayonet blades, that was fine. That standard was fine, okay? But other things, like I don't want you to do the whole structural welding code or something, or the pressure vessel code, because it'd just be, in 10 minutes, how could you cover something that's 32 volumes, right? In terms of, you know, how it evolved, what it covers, does it have force of law, what other codes does it call out? Well, a 32 volume code calls out thousands of other things. A simple little code, like a code for making a piece of steel pipe, okay? Like A10, this would be A53 actually, this is welded pipe. But that's manageable, okay? It might call out another 20 codes. The problem is those other 20, not 20 codes, but 20 other standards. Those 20 other standards are going to call out another 15 or 20 standards each. And so things start multiplying until they start converging eventually. But anybody, no other questions and things? I wanted to talk about a couple things that Dr. Belmar talked about. He mentioned just in passing about this trailer that he designed, and the fact that he didn't have to worry about, in other locations, he didn't have to worry about the welds because he used bolts. Well, it turns out using bolts is actually required by certain standards if you're actually doing trailers, okay? The big semi-trailers that go down the highway and stuff. They require that you not weld on the frame. So the frame, if this is your truck, okay? Not a very good truck. And you got the trailer here. There is a frame, there are two frame rails, and they're sort of C-shaped pieces of steel like this. If you ever look at the back of the truck, this trailer that's going to, or this tractor that's going to be pulling the trailer on a tractor trailer, there'll be two frame rails looking at it from the back, and these are just formed pieces of steel, okay? And they go, you know, like that, right? Hopefully you're getting some idea of the geometry of two C-shaped sections. They might be half, 3/4 inch thick steel. It's pretty heavy steel. There are load limits on the highways because they don't want to destroy all the asphalt roads, okay? I mean, only place I see really heavy loads is in Michigan. Anybody from Michigan? Okay, you've been to Michigan. You've seen the 48-wheeler tractor trailers. Well, no, this isn't tandems. These are, because it's the big automotive area, and they will put 4 or 5 rolls of sheet steel, which is probably 150 tons, on one trailer, and they will distribute the load because there is no space. If you go all the way back on that tractor, it's just, you know, 4 wheels, and if you count it up, it's like 46 or 48 wheels on this tractor trailer, okay? I mean, most of the tractor trailers you and I know in Massachusetts or Connecticut or New York or Pennsylvania are 18-wheelers, okay? Some of these things in Michigan, I've never seen them anywhere else except Michigan, are 46 or 48-wheelers, I can't remember. But something like that. Anyway, you want to reduce the weight. And so they actually use a high-strength steel, 100 KSI strength steel. And you can weld to 100 KSI strength steel, but the fatigue strength is terrible, okay? And I think I cover that somewhere in one of the joining courses about you don't get a significant increase in fatigue strength even though you're using higher strength steel. You tend to get the same fatigue strength as if it was lower strength steel. So this is clearly a fatigue loaded situation with the trailer bouncing, you know, the weight of the thing bouncing up against the frame rails. And they will have, if they have holes, they will have actually punched out holes in these things, and they will bolt to them. And the reason they don't have welds is because historically people have found that fatigue cracks start and they don't get noticed, and all of a sudden the trailer's going down the highway and it breaks in two. It's not a good day. So in any case, there's that particular problem with welding to these things. And why is it? It turns out the welds are actually stronger than the bolts on average. If we look at strength and we look at the number density, okay, of things, the bolts, if we look at a probability plot, and Dr. Belmar was kind of talking about probabilities for safety factors, but this is a strength probability, okay? A bolt has a fairly well-defined average strength, but a weld may have a higher strength. So the mean strength of the bolt is less than the mean strength of the weld, but the minimum strength, there's going to be some cutoff here, the minimum strength of the weld, because welds tend to have more defects, or can, is lower than the cutoff for the bolt. So in a sense, the bolts have less variability, even though they have less strength. You can predict statistically the capacity or of the bolts better than you can the weld. So there are codes for designing tractor trailers that don't allow you to weld, and most of those have been adopted by states and have the force of law. Because, I mean, the states don't care until they actually have some trailer fatigue on the highway, spin out, kill somebody, or tie up traffic for 4 hours or something, and then the state police get involved and they start investigating and figure out the reason, and they will then incorporate that somehow into some legal requirement, okay? But that was just sort of an example. As he mentioned it, you know, he was designing this trailer for his farm up in Canada or whatever, and I guess that's where he was designing it, I don't know. And he kind of knew to use bolts because, and it was sort of, I bet that it's sort of intuitive, okay? That he knew you don't use welds where you really have, if you have to have a certain level of strength, you can use welds like pressure vessels. You don't want to bolt together a pressure vessel because big thick pressure vessels 4-inch thick, you couldn't even build them if you didn't weld them. But you're going to spend as much on quality control and non-destructive testing as you do on fabrication and making the welds. Whereas on a trailer, well, who's going to spend all that money? You're going to take it out and have the welds x-rayed, you know, or magnetic particle tested? No, you're just going to make it. In fact, I actually call them horse trailer welders. There's a significant number of people in the world who learned to weld growing up on the farm, okay? And you learned to weld on a farm in a rural area. And so they know how to weld, but they don't know the science behind the welding, and every now and then they do something stupid. And I always remember one of my favorite stories is a guy brought a weld to me once, and it was from a trailer. It had been made up in Nova Scotia, and you got the A-frame, or you know, this is the hitch right here, and here's the frame, and right here in the corner they made a weld, and they basically cut and formed the angle iron of the steel or the C-channel or whatever it was, and they had a gap in there, so they threw a bolt in there to fill the gap, and they welded over the bolt. Well, that's actually known as slugging a weld. It was very common in World War II when they're trying to build Liberty ships and stuff. Someone was bored, and they were not necessarily Liberty ships, but on battleships and stuff, when you're welding 16-inch thick armor plate. It's really dull putting 600 passes into the same little section of weld, okay, when you're welding something 16 inches thick. And so people, so they get a little break, they might take a piece of pipe, or they may take a bunch of welding electrodes themselves, and they just throw them in the hole, in the groove, big groove, and they'd weld over them. And no one could find it because they're buried between several inches of steel in this old armor plate. But it did sort of weaken the whole thing. I mean, it's like making perforated steel, right? Slugged welds was always something we used to joke about because it went out with, after World War II, when people started seeing this, no one would ever slug a weld. I had never seen a slugged weld until they brought me this piece of a trailer. And the story with this trailer is this person lived on a farm, or they bought the trailer in Nova Scotia from a farmer who had built it for them. And it was a trailer for their sailboat, their 40-foot sailboat. And they had driven from Nova Scotia with their sailboat all the way down to Newport, Rhode Island for the races in Newport. And they had won the race, okay? And they were coming back up, it's not interstate, it's Route 24 or whatever, coming up from Rhode Island. It's like an interstate highway just south of Boston here. And they're cruising along about 55 or 60 miles an hour with their trailer behind them, and they hear a bang, okay? And of course they kind of slow down and they put their brakes on, and there's a sailboat, look just like theirs, just passing them on the highway, okay? Because the weld broke, okay, right here. The trailer let go, okay, and this, all of a sudden you had a freewheeling trailer and 40-foot sailboat, and it crashed and destroyed the sailboat, okay? And they brought me the weld and said, what's wrong with this weld? They wanted to go back to the farmer who had welded up the trailer and complain to him. I said, well, I mean, it wasn't hard. You saw about a 3/4 inch bolt that had been put in there, and just little welds were put on top of it, okay? So it wasn't a fully welded joint. It's called slugging a weld. It's the only time I've ever seen it, okay? But, you kind of look at this level of engineering in things, and you sometimes wonder about it. So far as that level of engineering, another bolted thing, which we found the other day when we were cleaning out some junk downstairs in the basement, we found this. This is, we called this Tron Air in the old days. This little bolt is part of a system to take a jet engine off the airplane wing. Okay, you have this kind of sort of a roll-up dolly that's about 15 feet tall, and you roll it up to the wing. You put this bolt into the hanger for the thing that holds the turbine engine on the wing, and you torque it down. You torque it on this side, then you torque it on this side, and then you just pull it out. You release the bolts that held it on the wing, and you pull it out, and now you have the jet engine that you can now work on as a mechanic. So they were doing this, and the guy who designed this designed the centerpiece with flats on it. You can see the flats. I'll pass it around. You can look at it. So you could grab this thing with a pair of pliers. And if you grabbed it here with a pair of pliers, you could torque this to the proper torque for this size bolt. This is a hardened steel bolt, okay? This thing probably is a $200 bolt, okay? It's specialized. How many of these do you need? And the other side, they had a different size thread, and you were supposed to grab it here and torque here. Well, they actually torqued it here, and they didn't bother to grab it here. They just felt, well, we torqued it here, they held it with the nut here, and they torqued here. Well, look at them. The two of them are different diameters. It turns out the proper torque for this is just enough to start a crack in this, okay? So you have to worry about your what we call the load path. If the load path was only from here to here, and there's no stress on this when you're doing the torque of the large diameter, what's the problem? However, if your load path it just ignores this little shoulder, and you don't grab it and keep it restrained, now your load path goes all the way through to the other nut, and all of a sudden you over torque this thing. Okay, so in hindsight, after they dropped an engine on the tarmac, okay, and it cost about $5 million. Engines are not cheap. They looked at it and said, "Ooh, not a good design." And so I mean, simple little things, and I'll show you another one a little bit later of a load path problem, okay? But one of the things I want to talk about today, we've talked about measurement and codes and standards. I wanted to talk about design and the types of design. We often just talk at the university, well, you're supposed to have a capstone design course as an undergraduate or something, okay, where you can show your creative energy. And one of the things I wanted to do in this course was to point out to you that your creative energy is limited by codes and standards. You're not free to just go out and do whatever you want. Good manufacturing practice basically tells you that you shouldn't just do whatever you want. You should follow the experience of other people who have learned through sad experience because of failures that have caused a lot of property damage or other things. And so design is actually a complex process. People teach whole courses on it. And it turns out there are different levels of design. And in different businesses, you might come up with different lists. But if you were building a bridge or a building, you usually start out with something that we often call the conceptual design, okay? And the concept is, well, we're going to have a bridge across the Charles River. And if you look at the Mass Ave bridge, it was going to have walkways on either side with certain type of railing, and it was going to be low to the ground. It wouldn't have domes or something, and it's going to be made out of steel. And that's the Mass Ave bridge. If you look at the Longfellow Bridge, it was built a few years earlier. It's all made out of stone. It has the salt and pepper shakers as the columns and stuff. That's the concept. It's sort of, the conceptual design could be as simple as someone just sketching it out on a back of an envelope, okay? This is what I want my bridge to look like, or this is what I want my building to look like. It's going to be, you know, pyramidal shaped rather than box shaped building or something. Okay, that's, you just kind of sketch out a concept. This is a conceptual design right here. I just crumpled up 4 sheets of paper. Anyone who hasn't heard this story before, does anyone know what that is the conceptual design for? Now, do you know this concept? You know the story? The Stata Center. You know the building over here that has all the weird shapes and stuff? So I know this story for a fact because Vicki Sirianni, who's she's an architect and she was head of MIT Physical Plant. And they were about to build the Stata Center, and they hired Frank Gehry, who's one of the world's renowned architects. And I happened to meet with her the morning after she got back from Los Angeles, meeting with Gehry in his office. And she was in a conference room with some of the other people, and Gehry walks in, and he starts crumpling up paper, and he throws it on the table, and he says to her, "That's what your new building's going to look like." So there's the conceptual design of the monstrosity we call the Stata Center, okay? Crumpled paper, okay? So there's all kinds of levels of conceptual design. And if you're one of the world's renowned architects, you can just throw out the biggest piece of bullshit, okay, in the world and call it a conceptual design. And you leave it for your underlings to work out the architectural design, okay? But the concept was we were going to build this $400 million building. Actually, it was supposed to be $115 million. That's another story. But it went over budget a little. It came in at $430 million. They froze everybody's salary at MIT for 2 years, okay, because they were so far in the hole after, you know, going over budget by a factor of nearly 4. Anyway, that's another story. Probably not worth telling right now. But conceptual design can be, you know, actually today conceptual designs are often done on a CAD system, and you kind of get a nice little rendering in 3D, you know, kind of imaging that you can rotate and everything else. And someone does, but it's still sort of a boxy design, and it might show you where the windows are in a building and the entrance and, you know, some of the sculpting around doors and things, but it doesn't give you a lot of detail. The architectural design, what's the architectural design involved? You're a civil engineer, Steve.
Well, the architect just gives us something and we stand up.
Well, the architect tells you how many square feet it's going to be, where the rooms are located inside the building. I mean, Gary didn't have to worry about where the rooms are, okay? He didn't have to worry about the details of the design that you walk in the lobby of the Stata Center, most expensive building on campus by far. And what do we have in the lobby? We have concrete block walls and concrete floors, okay, right? But everything's sort of, well, I guess the word is catawampus, if you know what catawampus is. Nothing has square corners, you know. It's crumpled paper, right? But some architects, I'm sure a whole team of architects probably charged MIT $40, $50 million for their time, worried about how to make the, you know, what the shapes were, where they're going to put the doors and all the windows, and which windows are on a sloping wall, so they have to have an extra frame because they got to be vertical windows on a sloping wall. Go look at the thing, it's a monstrosity. Anyway, but some people love it. It's sort of like politics, you know, you're on one side or the other. Some of us think the Stata Center is a disaster. Anyway, so the architectural design goes through things about, oh, this is where the doorways are going to be, we're going to put the restrooms over here, we're going to put the big lecture hall here, you know, that's the architectural design. It's kind of, these are the pieces of the Lego system that are going to build up the whole three-dimensional object of crumpled paper, right? So what's the detailed design? Come on, you've worked on detailed designs. Detailed designs, those are the engineering drawings. Rather than an architectural drawing, which kind of shows you the layout of the building. I mean, you've seen the architectural layout of a home. It says we have a bedroom, master bedroom here, family room over here, fireplace here. But the detailed design is something that actually starts telling people where you're going to have 2x6s, where you're going to have 2x4s, where you're going to have a steel beam to hold up some cantilever or whatever. That's the detailed design where engineers, not architects, but engineers are actually doing calculations on the stresses on beams. But those guys don't necessarily, there's actually often two sets of detailed designs, or so maybe two sets of architectural designs on a complex building, or two sets of detailed designs. Sometimes they call something, rather than detailed designs, in here they call it shop drawings. Anybody know what a shop drawing is? So the detailed design, the engineer says, he's a civil engineer, he says, well, we need a 2x6 here, we need 2x4s over here to hold up the floor, we need a joist, you know, here, a fabricated joist to hold up the ceiling or whatever. But he doesn't tell you how to build it. Okay? He might tell you it's going to be made out of wood because he had to figure out the strength based on wood or steel or whatever. He had to do the properties, but he doesn't worry about things like how do you join it together. If it's a wooden beam and you got the A-frame of a roof, how do they join it? They used to use nails. Well, actually, if you go back far enough, they used to use pegs, right? Wooden pegs. Now, the finest construction is wooden pegs, but 400 years ago, they used wooden pegs because nails were too expensive, okay? But nails got to be cheap with the coming of Andrew Carnegie and steel becoming cheaper. And so they quit using wooden pegs, which are very labor intensive, and they started using nails. They don't use nails nowadays when they make up one of those flat roof trusses. What do they use? Punched metal plates. They take a piece of galvanized steel, they punch it so they make little triangular shaped cutouts so that if this is the plate, you'll put a triangular punch, and the pointed triangle is sticking through. You may have 50 of these things or 100 of them, and you just put it on the joint. So you got to, if you've got a 2x6 running up this way, and you got 2x6 this way, you may put one of these galvanized plates with all these punch marks in it that you just lay it on here, and then the guy pounds it down with a mallet, and all these little nails, if you will, which are just punches of the sheet metal, all go in there, spread out nice and uniformly. Great distribution of stresses compared to toenailing at some angle in here. Labor savings, all done in the shop. You lay this out on a great big table, flat, put it on a truck and take it to the site. The crane drops it in place. Okay? Which gets you to the next thing, is the erection drawings. So I've been driving in, and I come in down Broadway and come across on Galileo Galilei, which is over here by the Whitehead Institute. And somewhere behind the Whitehead Institute, they're building a new building. And you got some really big steel beams. I mean, these things are like 3-inch thick flanges, 4-inch high webs. These things are real. I don't know what they're building back there, but they could store M1 tanks, okay, in whatever they're building there. Really heavy stuff. But I can't really see what they're building because it's down behind a bunch of other buildings. There's nowhere to bring all of these things all at once to the building site. So you got a logistical problem. If you were building this out in the middle of Kansas in some field, you'd have what they call a laydown yard, and it doesn't matter. The fabrication shop that does the shop drawings tell you what welds to put where. Okay, so the detail drawings may tell you what shape beam or what shape steel, but the shop drawings will say, put a fillet weld here, you know, 1/2-inch fillet weld, and continuous or intermittent or whatever. There's lots of details on a shop drawing that tells the guy out there in the shop where to put the welds and what the size pieces are that it's going to put together to make up these beams. Well, anyway, over here they're building this huge thing. In the erection, they have to keep track of every beam, and they can't store all the beams in a field and just go out and get the beam they want when they want it. When I drive in, there's usually 2 or 3 trucks parked there right beside the Whitehead Institute with these huge beams on them ready to unload. And so it's a huge logistical problem of making sure the right beam arrives at the correct time, because you have no storage space. Once it gets there, it's just-in-time erection, okay? And they have bolting plates, and they bolt them together in the field. They may weld in the field, whatever. And they're supposed to build it a particular way. But they don't always build it a particular way. Just because the erection drawing says this is how you're supposed to build it, or the architectural drawing says you're supposed to build it this way, sometimes for some reason there's a change. And you don't always see this in a job that's trying to, and this could be building a nuclear submarine, okay, as opposed to a building, okay, building anything. They will actually go in afterwards and have an architect or engineer do a whole new set of drawings called the as-built drawings. How do we actually build it as opposed to how we thought we were going to build it, okay? And that's just in case later you need to get in there and do something, because people have found when they're doing repairs on things, they have some problem and they go back to the original drawings and they come up with the correction based on the original drawings, and then they get down in the bottom of the ocean on an oil rig or something and they find out, oh, they didn't build it that way. Just because we have the drawings, that's not the way it was really built, and everything they just spent $1 million putting together doesn't fit because it wasn't built the way the drawing said. So many times you'll have a set of as-built drawings. So there's a whole series in the whole process of design. It's not design is not someone sitting down and laying out the final set of drawings. There's a whole hierarchy of these things. And in fact, in building something like a nuclear submarine or a Boeing jet, a new Boeing jet, you can spend $1 billion just doing the drawings. And it used to be in course 2N, which used to be course 13, they had a whole group of people for shipbuilding 15 years ago, 10, 15 years ago, when computers and CAD designs were getting more sophisticated and more powerful, that they could have a virtual walkthrough in a building or a nuclear submarine. Where are you going to put the piping, the ductwork? Where the electrical cables are going to go? Because in the past on a nuclear submarine, you'd have some guy designing the electrical cables, and he puts them right in the middle of the ductwork, because the guy who's designing the ductwork is putting the ductwork where he wants it to go, and he doesn't worry about the electrical cables. And so you get down in the middle of the ship, at the shipyard, and the guy says, this is impossible, I can't build it. Okay? And that's why they would modify it on site. It would double the cost of a ship. And it turns out when they designed the 777, I think that was the first Boeing aircraft design that was entirely designed on the computer. I know certainly that the new digital, they called it the digital 737 after the 777. The original 737 design was a huge number of drawings. They had rooms full of draftsmen just sitting there making drawings for this aircraft, the old 737 back in the 70s. And they got updated, and they had to have this library of what's the latest drawing. I mean, I've been to Bell Helicopter, and you know, you ask, well, can I see the drawing on this? They have to go through a library going back 30 years to figure out what drawing applied at this time when this helicopter was built, because the drawings change over time. It's not a constant thing in manufacturing. The drawings for automobiles are just horrendous in their complexity, okay? The contours and the shapes. I mean, you like the nice aerodynamic design of an automobile. Well, the drawings on that just make that very difficult to do. In any case, having a huge database where you can check, and this was one of the mathematical problems of in these CAD designs, to see if you were putting the electrical cable or the drainage pipe through the air duct, because you don't really want, you know, big holes in your air ducts. They don't work so well. You don't want electrical cables going through your sewer pipes, but that's what they would have. And so one of the mathematical things was for the computer to find where things were intersecting when they shouldn't have been intersecting, okay? And that's not necessarily the easiest problem. It's sort of standard practice today, but 10 or 15 years ago it was not standard practice. And so today they design most complex things. Very detailed designs. The detailed designs are done in a CAD system. And so you still have a whole group of draftsmen, but they are computer draftsmen, IT engineers more so than the guys with pen and paper and whatnot.
All the CAD files for the Corvette Z06
Yeah.
are 8 terabytes.
8 terabytes, okay. Well, they used to say that the paperwork, now this is not the drawings, this is just the quality control paperwork, and you know, that occurred during building of a 747. The paper weighed more than the 747, okay, and had to be stored forever until that aircraft went out of service 30 years later, 20 years later. Now it's all stored on some disk somewhere in a digital form. Okay, so there really has been sort of a revolution in manufacturing, from aircraft to nuclear submarines to automobiles to whatever. It's sort of amazing what's happened. And there's a whole set of standards on how to do, that have developed over the last 15 or 20 years on how to do those types of things. Okay. Well, let me give you an example of an as-built that didn't quite do it the way, and caused a serious problem. And this is the Hyatt Regency Hotel in Kansas City. On July 17th of 1981, if people have been to Hyatt hotels, they know they have these big, tall atriums. I lived in Atlanta, Georgia, as a teenager, I think, when they built the Hyatt Regency Atlanta, which was the first big Hyatt Regency with a big atrium. That building is still there. They built a bigger Hyatt right next to it. The old one was only 40 stories tall. I think the new one's like 60 stories tall. But people still go to the old one to commit suicide, okay? They go jumping off the balconies, and so you're sitting there eating your breakfast, well, you know, at the restaurant on the atrium floor, and all of a sudden someone comes splat right next to you. Actually, it doesn't happen that often, but this was one of the big things. I mean, I remember as a teenager, well, I was just barely a teenager, okay? Because I moved from Atlanta when I was 13 or 14. But anyway, I remember in the newspapers, this big 40-story atrium was, people would just come, and I think my parents, we went down to see it. Everybody in Atlanta had to go see this atrium, and this was their selling point for the Hyatt Regency. And then about 6 months later, people started using it as a place to kill themselves. But nonetheless, the Hyatt still liked to build atriums. If you go to Hyatt in San Francisco, big atrium, you know, most places. And they had built one in Kansas City. And the one in Kansas City, they decided to have walkways going across the big atrium. So you had this ring of balconies outside the rooms. And actually, some of the suite hotels have the same type of design with atriums going 10 stories up now. And in fact, they may be a spin-off of the Hyatt chain now, but nonetheless, they decided at the Kansas City that they were going to have walkways that might take you from the 10th floor down to the 8th floor, and you could cut across 180 degrees across the atrium. And so they had a series of these at different angles, and this was sort of artwork up there. And so on July 17th, 1981, it was a Friday night. They were having a party, and there was a big band, and the whole atrium was just a huge party scene. And there were a bunch of people on these walkways going across the atrium, 10, 15, 20 stories in the air, kind of dancing to the music and stomping their feet. And then all of a sudden, all these walkways started to collapse, and 114 people died and over 200 were injured. And so the Kansas City Star won a Pulitzer Prize for tracking down what really happened in the design. And so here's the thing from the Kansas City Star. By the way, this comes right out of Petrossi's book, To Engineer as Human. And when he wrote the book in, when did he write it? 1982, so, but it's updated 1986 or 87. Some of this was still in litigation, but what happened was the architect who had designed it decided they were going to have a hanger rod. I don't remember if this is 3/4 inch or 1 inch steel rod. You know, 1 inch steel rod might hold 50 tons in theory, and if you put a safety factor on it, and this might have been a building safety factor. If they used the structural welding code, they wouldn't use the welding code because it wasn't welded, but nonetheless, they might have used a safety factor of 1.67 for the steel. It should have been a factor of 2 safety because it's dynamically loaded, right? This is not just a static building. This is something that could be swinging out there in the atrium, so it's fatigue loaded. But anyway, the detailed design basically showed a rod that had 2 C channels that had been welded together, and the rod would go through here and have a nut on the bottom that would hold the C channel that held the walkway. And there were a number of these rods hanging down. The only problem is this was supposed to be a solid rod. It wasn't a threaded rod. How do you get the nut on? Well, you could have threaded all 15 feet down to the next walkway, but who wants to sit there and turn the nut for 15 feet to get it at the right position? No one had ever stopped to think about a shop drawing of how you're actually going to, or an erection drawing of how you're actually going to make this. So in the field, they said, I can't make this. What idiot designed this? Okay? So they decided they would just fix the problem, and they'd have 2 rods. One rod hanging down with a nut up here and another rod coming through here with a nut on the bottom. Solve the problem, they can erect this. This is as built. this was designed. Turns out in the management of this whole stream of design, anybody makes a change down here has to submit it to the people up here to have them sign off on it. Well, in a big complex building like this, there are thousands of changes, and they have to be signed off on them. And frankly, if you've ever been involved in one of these things, people will go, you got to get it built, and you make the change that day, you submit the drawing, and it gets approved 3 weeks later by the architect. And under the law, the architect in most states has to be a registered architect, and the engineer, something called the engineer of record, who's responsible for the detailed design. You got an architect here for the architectural design. You got an engineer responsible for the detailed design. He could have 100 engineers underneath him, but he has to be a professional engineer. He has to be licensed by the state, and he puts his seal on there, okay? That he has checked it, and he knows that this design has been it's calculated and checked, and it's a good design, that it has enough strength. Well, it turns out it either got done late or people just missed it among the thousands of details that were coming in for changes, or the person had no experience. I'm not sure they ever figured out exactly what happened. Certainly no one was coming forward to say, I did it, after 114 people died. But what happens here, the load path here is going, on the original design, was going straight through the steel rod. Here the load path goes through the rod, takes a dog leg over, and then comes down through the other rod. And as Petrosky says, well, think about it, if you had two people hanging from a rope. That's interesting. So you got a rope, and you got a person up here hanging from the rope, and you got another person hanging from the rope down here. All you have to have is a rope that can bear the weight of two people, right? But if you had a rope coming down with a person on it, and then this person was, you tied a rope to this guy's leg, and that person was on there. Now it turns out that person's leg is bearing, or this rope is still just bearing the same weight, but this person's leg becomes the weak link, okay? And it turns out that's exactly what happened. The weak link was between those two bolts in the staggered system. And that basically sheared rather than a straight tensile pull. You change the entire load system with that small little change. The guys erecting it, they didn't think it was a big deal. They figured, oh, I can make this, I can make the other, whoever designed this is impossible. And there's lots of design foibles. I mean, there was, I think it was the 1978 Chevy Vega that, they build the whole engine and they put the engine into the frame of the vehicle, and it turns out when you needed to go change the spark plugs on the Chevy Vega, you had to remove the engine because some of the other components were blocking it. It was impossible to get a wrench in to remove the spark plug. Well, in the plant, it was no problem. The spark plugs were already in the engine when they put it in the vehicle. But no one ever bothered to check, could you ever service that engine? Okay? So there's little details that you have to worry about the whole system going forward. Well, the Hyatt Regency was the as-built was not like the as-designed. And of course, there was all kinds of finger pointing, so far as that goes. Another story out of automotive that I ran into, it's 90 or 91, I bought a Ford Taurus. And turns out, I bought it in February, never turned the air conditioner on in February for whatever reason. Come May, I turned the air conditioner on one day, doesn't work. Brand new car. Well, I mean, not brand new anymore, 4 months old, but still under warranty. So I take it to the dealership. They said, oh, we don't have the parts to fix it. I said, fine, give me a new vehicle. I don't care, okay? Because under the Massachusetts lemon law, all I have to do is bring it in 3 times to have them fix it, and if they can't fix it within 3 days, then I can get a brand new car. I did that to General Motors once in 1985 and got a new, they had to buy back my car because it was a van and it had a sliding side door, and the door fell off 5 times, okay? You know, one time I had them come tow it out of my driveway because I didn't want to drive it over to the dealership. The door was just kind of hanging by sheet metal, right? And I was not trying not to go lemon law on them, but the owner of the dealership wrote a nasty letter to me telling me it was my fault. I said, okay, I could have done lemon law after 3. Now it's 5. Here's my lemon law demand. And General Motors came in and said, what do you want? You want us to fix it, or you want a brand new vehicle? Or I said, I just want a van. I wanted to go on vacation with my family that summer in 2 months. And they said, okay, we have this, you know, executive vehicle, you know, the one that they let their people drive for 5,000 miles and then give you a discount. We'll give you another one, you know, as soon as this is available. And it was supposed to show up like in 3 weeks. Well, they called me up and they said, sorry, the executive hasn't finished with it. We'd rather give you a check instead. I said, well, I really wanted something to go on vacation. So they gave me a check. I went out and I bought a vehicle off the lot at another dealership. Okay, not the same vehicle, but anyway. The problem with the Taurus was that they had a problem with all their air conditioners. The design of the air conditioner, they had come up with a wonderful design that had just one sliding shuttle going back and forth. And so, you know, in air conditioner, you got compressor to compress the Freon and then expand it and stuff. And they had this simplified design, but it had very, very tight tolerances on the shuttle going back and forth because it didn't have the same types of seals that were in most air conditioners of prior design. So they had very, very tight tolerances. So the engineer or the engineers who had conceived this, they decided, well, when we machine this, we're going to have the proper fixturing so that when we clamp this thing and then machine it and then unclamp it, we don't lose some of our tolerances. Okay? Makes sense, right? So they sent this out for prototype development. They had the drawings, showed them not only how to machine it and the dimensions, but they also showed them how to build the fixture to clamp it when you're doing your machining. And they get the part back, they test it, works great, decide to build a $100 million facility to make these air conditioner compressors for the early 90s Ford Taurus. And I happened to buy one of these early version air conditioners, which turns out it didn't work. And Ford had been learning, because there were probably people who bought it in February in Arizona who now were turning on their air conditioner in March, okay, that it wasn't working. So Ford had been learning that it wasn't working. And they went and fixed it. But as they were researching it, they were trying to figure out why it wasn't working. And they found out, they went to this machinist who had done the prototype clamping and everything and said, well, did you clamp it this way? He said, oh no, I knew that wouldn't work. I designed my own clamping arrangement. And so he designed a clamping arrangement that worked. But they didn't know that. They didn't know the as-built of the prototype, okay? They built a $100 million facility with tens of thousands, if not hundreds of thousands of dollars of clamping fixtures that were wrong, okay? That this machinist knew better, okay? And so they had to retool their whole line to put in the proper clamping so that they could get the tolerances they needed on the machining to make the air conditioners work. Well, in my case, by the time I find out in May that my air conditioner is not working, they're way behind, and all their production of these, you know, major rapid improvement of their screwed up stuff is going to production models, right? Because they can't sell a vehicle in May that in most parts of the country that doesn't have air conditioning. Maybe in North Slope of Alaska, but not in the continental United States. Everybody wants an air conditioner, right? And so I come in for a repair and they say, oh, we don't have anything. Well, it'll be in July. I said, well, give me a new vehicle. And they said, well, we can't. I said, well, give me a whole new air conditioner. And they said, we can't. I said, well, give me a whole new vehicle. At that point, and I said, I also know some vice presidents at Ford, and I'll be happy to call them if you like. They found me an air conditioner, okay? And I'm sure it probably slowed down someone's delivery of ordering a new vehicle, right? Because I got one that would have gone to the production line to sell new vehicles. I actually didn't know that full story until the guy who later became dean of the Harvard Business School actually told me some of this other story. He had been studying Ford, and he had heard about this story. I knew what had happened to me, that they wouldn't give me an air conditioner, and they were telling me I wouldn't have an air conditioner for most of the summer that year, and I said, nope, not acceptable, okay? But the real reason was because some machinists knew more than the engineers, which is not uncommon, okay? So that's the moral of that story. Okay, I'll see you tomorrow.